a Portland Community College Mathematics telecourse. A course in arithmetic review, produced at Portland Community College. This lesson will tackle the problem of adding two fractions that are not like fractions. What to do? You know, even if this were not a review course for you, I'd bet that you would probably know what's going to be done. If so, then you are beginning to think like a scientist. That is, you're asking, what have you known before this that would relate to this problem? You'd probably tell yourself, I can't add until these are the same. But through fraction building, I can make these be many, many things. So I ask myself, what's the one number both of these will divide into? That is, what's the least common multiple of these two? And that, of course, is 12. Then you would say, well, I could build 3/4 to 12ths by multiplying top and bottom by 3. And I could build 6 to 12ths by multiplying top and bottom by 2. So my two fractions have been changed to equivalent fractions, 9/12ths and 2/12ths. And now the denominators are the same. They're like fractions. So my denominator stays the same. And I add the tops. Check to see if it's reduced. And I'm done. So in principle, adding fractions with unlike denominators are simple. Simply get them to have common denominators, then go ahead and add. Again, to add unlike fractions, build them to have common denominators, then add. Then check to see if reduction is possible. Quite frequently, one can simply see what the least common denominator will be. In this case, what's the least number that these three will divide into? And of course, we can just see that it's 30. And in this case, we'll build with a factor of 6 to get 30. This already is 30. And here we'll build by a factor of 5 to make it 30. And my three fractions now become the three equivalent fractions, 12, 7, and 5/30ths. But since the denominators are now the same, we keep it the same and add the numerators. So this is 12 plus 12 is 24, and this would reduce. 6 goes into 24 4 times. 6 goes into 30 5 times. So 5/4 is the sum of these two fractions. Most problems the average person runs into will have denominators so simple you can just see it. Most of them. However, in technologies and engineering and sometimes business, it isn't quite that simple. But first, let's answer the question, what would have happened had we not picked the lowest common denominator, which is 30? We could have picked 60 or 90 in this case. In such a case, and as a matter of fact, any common multiple of the denominators would work. But any but the lowest will always present you with more reducing on the answer than you would encounter otherwise. In short, you would simply get more work to do, and that's something generally we try to avoid. Now here's a beast of a problem that most people would feel they couldn't do. But it really reduces to just this. How do you find the lowest common denominator given enough time to work with it with a calculator or however you wish? Now with your background so far, this should be a very routine problem. However, it will take a bit of time. Could you instruct a friend step by step through this problem? What would you tell them to do first in finding the least common multiple of those three numbers? You tell them to prime factor each denominator and express each prime factorization in exponential form. Let's do each one very quickly as one last review. Factoring, or by repeated divisions by prime numbers, we would get that 196 is 2 to the second power times 7 to the second power. So let's write that 2 to the second power times 7 to the second power. And by repeated divisions by prime numbers into 616, you'd find 616 is 2 to the third power, 7 to the first, 11 to the first. So let's express that. And finally, by repeated divisions by prime numbers into 182, we get that it's 2 to the first times 7 to the first times 13 to the first. So here we have the three denominators in prime factored form. Now what would you instruct your friend to do next? List all the different bases as factors to be. So let's see, I've got a base of 2, I've got a base of 7, 11, and 13, putting them in sequential order. Then you would tell them, give to each of those listed bases the highest exponent used. So on the base 2, there's a 2 there, a 3 there, a 1 there. So the 3 was the highest one used. On 7, there's a 2, 1, 1, so 2 is the highest. 11 is 1, 13 is 1, so this is the prime factorization of my least common multiple, and in this case, my least common denominator. A terribly messy number if we were to multiply it out. As a matter of fact, its value is 56,056. That's the smallest number that exists that all three of these will divide into. There are many, many, in fact an infinite number greater than this. But this, as big as it is the smallest. However, we didn't really need to know that just yet. As it turns out, this factored form of the lowest common denominator also makes it easier to build the fractions. So let's just leave it as it is and watch what happens. Let's just observe and count. I want this to look like this. This one has 3 2's, this one has only 2. So I'm going to have to multiply it by one more, and I'll list it down underneath here. Okay, this has 2 7's, but so does this. This has 1 11, this has none, so I'm going to need one more 11. This has 1 13, this has none, so I'll need a 13. So in fact, to make this look like this, I need to multiply it by 2 times 11 times 13, both top and bottom. If I do that, the top becomes 286, that is that times that times that times 1, over the lowest common denominator, which is this large creature here. Now let's do the same thing for this one. I want this to be like this. Well, let's compare it to this. This has 3 2's, so does this. This has 2 7's, this has only 1, so I'll have to multiply it by one more 7. This has 11, so does that. This has 13, this one doesn't, so I'll have to multiply it by 13 to make it become exactly that. But then I have to multiply the top by 7 times 13. So I'd have 7 times 13, whatever that is, times 5, and this fraction would become 455 over that common denominator, which we'll just call LCD. Now just repeating this procedure, I want this to look like this. Well, this has 3 2's, this only has 1, so I need 2 more 2's. This has 2 7's, this is only 1, so I need 1 more 7. This has 11, this has none, so I need an 11. This needs 13, this already has it. So this is what I need to multiply bottom and top by to make the bottom become this lowest common denominator. So taking that squared times that times that times the top, I would get 924 over that messy lowest common denominator. Now note, I have a common denominator and an actual value. I don't know what it is except it's this. Actually we do, because we already multiplied it. But the point is, I didn't have to know what it is. So now our problem reduces to this. Since I have a common denominator, I need to only add the tops. In doing that, I would get this problem. Here's my lowest common denominator, just not multiplied out yet. Now I simply add the numerators to get the numerator of my answer. 1665 over this factored form of my lowest common denominator. But even here, I'm not going to multiply this out, because then I just have to reduce. Because in prime factored form, whatever this number is, and remember, in fact, it was this large number. In factored form, it's easier to see if this is reducible. Because in the first place, the only prime numbers that will divide into that huge number is 2, 7, 11, and 13. So even if we had a calculator, this prime factorization is going to help me. We can see that 2 won't divide into the top because it's not even. So we'll take the top, which is 1665, and just check to see if it's divisible by this factor, 7. I get a decimal, so it isn't. So I try the same top, which is 1665, and see if it'll divide by 11. So divide by 11. I get a decimal, so it's not divisible by 11. So I get the same numerator, try to divide it by 13. I get a decimal, so I know that is not reducible by any of these prime factors. A lot of other things will go into this, notably 5, but it must be a common divisors, and these are the only ones that divide the bottom. So we know that this fraction, and now if we want, we can multiply 6056 is indeed reduced. Now this might give you a little bit of a sense of power to be able to do this, because very few people can, and yet it's not hard. The reason they can't, they just have never learned how. It's messy, there's a lot of arithmetic, but it's very routine. That's a good point to end on, to show that even the messy fractions can now be done. So let's walk through one of everything we've done in the last few lessons so that in your mind you can tie it all together. First, if you're adding fractions, you scan the denominators and ask one question. Are they all the same? If they are, then that becomes the denominator's answer. Then we simply add the tops, either by hand or by calculator, depending upon your teacher's objectives in training you. So in this case, we'd have 23 plus 17 plus 16. And we have that the sum is 56/42. Then we scan it to see if it's reducible. So I can divide top and bottom by 2. 56, divide by 2 by hand or calculator. Then dividing the bottom as well by 2 in this case. Now we have a fraction which at first looks like it's reduced, but then note I can divide top and bottom yet by 7. 7 goes into 28/4, 7 goes into 21/3. So sometimes you think you're done reducing, but in fact you've omitted something. So always be sure it's reduced. Then if your fraction is an improper fraction, you ask whoever you're working this for Do they need the answer in improper form, or do they need it in mixed number form? And again, please note, we're not saying this is right and this is wrong. They're both good. They're both the same number. It's always a matter of which is preferred for whatever the use that's going to be made of the results of this problem. But the point is, the initial point, to add fractions, the denominators must be the same. It stays the same. You simply add the tops, reduce, then change to mixed number if that's what's desired. Then we moved on to the question of what happens if we're adding fractions whose denominators are not the same. Well, if they are not the same, as such, we do not have permission to add yet. But then we ask ourselves, what's the lowest number both 4 and 6 will each divide into? And that was 12. Or stated differently, we were finding the least common multiple of the numbers 4 and 6. But then we recall I can fraction build each of these into fractions of equivalent value, but which will now have, or then have, a denominator of 12. Or in short, we ask, 4 goes into 12, how many times? 3. 6 goes into 12 twice. But to correctly fraction build, I must multiply top and bottom by the same amount in each case. Therefore, this fraction becomes 9/12, which is the same thing as 3/4, just expressed in different form. And 1/6 similarly becomes 2/12. But now they have common denominators, which we got first, wasn't it? And that's what gave us permission to add the tops. And I have a fraction which is in proper form, and it is reduced. Very frequently when you add fractions, it will be in reduced form, but we must always check that it is. And very, very frequently in simple everyday fractions, the denominators will be simple enough you can simply look at them and see what that lowest common denominator is. But let's remind ourselves why we wanted the least common multiple. After all, although it is true that 12 is the smallest number that 4 and 6 will go into, they'll also divide into 24. They'll also divide into 36, as a matter of fact. In fact, there's an infinite number of numbers that each of 4 and 6 will divide into. And we could build each of these to be, in this case, 36. 4 goes into 36 9 times. And of course, I have to build top and bottom by the same factor. 6 goes into 36 6 times, so I build top and bottom by 6. So this gives me 27 36, and this gives me 6 36. So since they have common denominators, I certainly have permission to add. So 27 plus 6 is 33. And that is reducible. I can divide top and bottom by 3, and I get the same answer I had previously. And of course, it must always come out to be the same results, because these are the same numbers as these, just written differently, and different than what we had just preceding this. The point we want to make is that any common multiple would work. But if you use anything other than the least common multiple, you will always have to reduce. Whereas if it's a least common multiple, frequently you will not, and always the reducing will be simpler. So the least common multiple will give you also the least amount of work to do. Then we moved on to addition of fractions where the denominators are not only not alike, but mentally it's not so easy, possibly impossible, to just see the lowest number that each of these would divide into. So at this stage we hope that now you see why the method for finding the least common multiple has been reviewed so frequently in past lessons. Because if it has, then at this point you notice there's going to be a lot of arithmetic, but it's not at all difficult, just a little bit time consuming. So going through the actual work on this with you from beginning to end, we begin dividing by the lowest prime number we can think of, over and over, until we've repeated by all the prime numbers we can. And that tells me that 48 in this case is 2 to the 4th times 3 to the 1st. Going to the next one and doing the same thing, and sometimes they're so simple we can do it mentally. We can see that 2 goes into 18 9 times, and 9 is 3 times 3, or 3 squared. Okay, same thing here perhaps. 42, well, 2 goes into there 21. Perhaps we need some paper to help us. And 21 is 3 times 7. So 42 is 2 to the 1st times 3 to the 1st times 7 to the 1st. And of course we don't have to write this little 1 up here, but sometimes it helps us to think. Now, to find the least common multiple is just this simple. List every base, that's 2, 3, 7. The highest power used on 2 was the 4. The highest power used on 3, the highest exponent, was 2. And the highest exponent on 7 was 1. Now, using this as our guide and using this factored form instead of the original place value name, we can force each one of these to be this just by a matter of comparison. I want 4 2's, I've got it. I want 2 3's, I've only got 1, so I need 1 more. I want 1 7, I give it to myself. So I'm multiplying the bottom in effect by 21, so therefore I must multiply the top by 21, which makes it become 110 over this bottom, whatever it is. Now I want to build this to look like this, so I need 4 2's. I only have 1, so I need 3 more. I want 2 3's, I've got them. I want 1 7, so I give it to myself. And 2 to the 3rd is 8, times 7 is 56. So the top becomes 7 times 56, or 392. See, it takes a bit of arithmetic here, but the principle is simple enough. You simply multiply. Okay, now building this to look like this. I need the 4 2's still, so I need 3 more. I want 2 3's, give myself 1 more. Want 1 7, I've got it. So again, 2 cubed is 8 times 3 is 24. So I've multiplied the bottom by 24. I multiply the top. If I do that, I get 264. Again, the arithmetic can be involved, but the principle of what I am to do is simple enough. Now that these are all alike, I don't even know what they are in place value name, but I do know that they're alike. I can actually look and count the factors and see that they're all alike. So now I simply add 110 to 392 to 264, and I get 766. Again, a bit of messy arithmetic, but the principle of what I am to do is simple. I am to add the tops. If it's messy, but I still add the tops. Now to reduce, I can see the only prime numbers that will divide the bottom are 2, 3, and 7. I can see that 2 goes into the top, so I'll do that. 766 divided by 2 is 383. But I have divided out one of these 2's, which will leave me now with only 3 2's. But I can see that no more 2's will go in, so I can try to see if 3 goes in. So 383 divided by 3, I get a decimal. So although 3 will go into the bottom, in fact twice, it won't go into the top. So then I try 7. 283 or 383 divided by 7, I get a decimal, so 7 won't go in. So I know that my denominator is 2 cubed times 3 squared times 7, and furthermore this will be reduced before I even get it. So 2 cubed I know is 8, 3 squared is 9, 8 nines is 72, and 72 times 7, well, even without a calculator. 7 times 2 is 14, carry the 1, 49, 50. So here I have my answer, and it is reduced. See how very, very important and useful that process of prime factoring and that process of finding least common multiple really is. Without that procedure, this probably would remain an impossible problem for you, as it is for most people. But now you've moved into a realm of being able to work a problem that very few people can work. Again, not because it's difficult, but because they simply haven't been taught, and now you have. Become quite comfortable and good at this addition, because you'll find that when we move on to subtraction, as we will very shortly, the principle will remain exactly the same. So that should remain an easy lesson if this has become an easy lesson. This is your math host, Bob Fennell. We'll see you at the next lesson. Good luck.